Into the meat and potatoes of reinforced concrete column design, interaction diagrams. And we've previously talked about the capacity of columns if the load goes right down the centroid or eccentricity is zero. The question we want to know is what happens if the moment is not zero? What if you have combined moment and axial load on the column? And the short answer is that you reduce the capacity of the column. Pn goes down. There's an interaction between moment and axial force, and that's why these are called interaction diagrams. It's the interaction between moment and axial force and how they interact and affect the capacity of the column. And what we're going to do is use basic principles to solve for M and P at failure. The key main concept is the strain at failure is 003 is what we're going to assume. We're going to establish the neutral axis, that is, just pick a neutral axis. And then once we know the strain at the far fiber is 003 and where the neutral axis is, we can calculate strains at the steel using similar triangles. We'll check these strains for yield. We'll calculate all stresses and then forces in the steel. We'll calculate the concrete area and compression and the compressive force. We'll sum up all the forces to get the axial load at failure, and then we'll sum up all the moments to get the moment at failure. And that's a lot to digest, so it's best explained in an example. In this example, we have a 24-inch by 15-inch column with bars at the two ends and a 2.4-inch cover, well, not cover, from the extreme fiber to the centroid of the steel. Okay. And we have F prime C is 3 KSI and Fy is 50 KSI. And what we want to know is when the neutral axis is at 8 inches, where I've drawn red and blue, so where it changes is 8 inches. When the neutral axis is 8 inches and it's at failure, what is P and M at that point? And because it's at failure, we're going to say that the strain at the far end, right here, okay, we're going to say that the strain right there is 003. Okay. And that's the definition of failure when the far fiber equals 003. We've given that the neutral axis is 8 inches right here. And if we know that that's 8 inches, let me draw it on the diagram. We know that's 8 inches. By similar triangles, we can get the strain here as 0021. Okay, you just do 0.003 is to 8 as the unknown strain is to whatever that distance is, 8 minus 2.4, so that's 5.6. You do similar triangles, you get 0021. You do similar triangles again to get this. 00501. And then what we need to do is to see if they're yielded. And so one way to do that is to calculate the yield strain. Take 50 and KSI, which is the yield stress, divide by 29,000 KSI for E and get the strain. Or what I've done here in this table, I've just taken that strain and I've multiplied by E, and I've got 60.9 KSI and 147.9 KSI. That obviously can't be because it yields, so If it's over 50, you just replace that with 50. That's, I find, the easiest way to do that. And the red is in compression because it's on that side of the neutral axis, and the blue is in tension. And so the steel that has a strain of 0021 is in compression. Oh, so I've got that backwards. Just a minute. Compression and tension. Okay? So now that we know the stresses in the steel, we can get the forces. And lucky for me, even though I had it backwards, C and T, they were both 50. And so there's 2.37 square inches of steel on both sides, and they're both at 50 KSI. So if you multiply 50 times 2.37, you get 118.5 kips. And so you have 118.5 kips in compression in the red and 118.5 kips in tension in the blue. And then you have the compression force. And remember that the strain, stress versus strain, looks something like this. That's the stress that's going to be on this. But remember that we're replacing that with the Whitney stress block. Or it's that's an A. Okay, where the depth of the Whitney stress block A is beta 1C, and so this is the first time we're really going to use the beta 1. And if you remember from the first week of lecture, beta 1 is 0.85, coincidentally the same as the 0.85 on the F prime C, for F prime C is for KSI and under. And so we have 0.85 F prime C is the stress. And B times A is the area. Okay. B is 15. Okay. This is 15 inches wide. And A is beta 1 times C. And we had picked C as 8 inches. So A is 0.85 times C. And you multiply that all out and you get 260.1 kips. And here's our free body diagram on the face of the column. These two 118.5 kips up and down, and that 260.1 kip up. So up is compression, down is tension in this picture. Okay, so we've got the forces, and once we get all the forces, we add them up to get the total P. And so you have that 118 up, 118.5 up, 118.5 down. They cancel each other out. So you have 260.1 kips is Pn. That's how much the column will hold at failure. And then you sum moments about the center of the column to get Mn. And so you have that 118.5 times 9.6 going counterclockwise. The other 118.5 times 9.6 going counterclockwise. And the 260.1 times 8.6. Okay, so that's just 9.6 minus A over 2. Okay, right here. Okay. And the 9.6 I got from the 2.4 from the edge to the steel. Okay, and that's, so it's 260.1 times 8.6. In this case, they're all going counterclockwise. This doesn't always happen. We'll do a couple different examples in class for your homework, but this is exactly what we're going to do for our homework, this exact calculation here. And we'll do it 3 different times to give you 3 different cases. But anyway, in this case, they're all going counterclockwise, so they all add together, and you get 45 12-inch kips. And so in the end, the combination of 260.1 kips and a moment of 45 12-inch kips. So that combination will cause that column to fail. Okay. Now, this was for a neutral axis located at 8 inches. If you change C, like to 10 inches or to 4 inches, or to, you can even have that 100 inches, these numbers change. And so you will get an infinite number of combinations of P and M that will cause that column to fail. And what I normally do in a class is there's 74 of you. I'll just figure out 74 different C's. I'll assign it to each of you. We would sit in the classroom, we would do this, and we would collect them all together. And then I would plot all your answers. And when I plot all your answers, it would look something like this. Okay, you repeat for different C's, calculate P and N, and you plot it. And what we would have, if everybody did it right, we would get 74 answers, each one with a different C, and it would be something like this. And every once in a while, somebody will have made a mistake and their point will be out there, and we'll know that that was wrong. Okay. And you do this, you collect all the points, and that's called an interaction diagram. It's the interaction of P and M. Well, in our quarantine, we're not going to do this. So what we're going to do instead, I'll just pick maybe 3 different C's, and we'll try it. And we'll get 3 points on the diagram. Now, on this diagram, here are some special points. This point up here, that point up there is pure axial. Okay. This point down here when P is 0 is pure moment, and that is T equals C, solve for A, Z is D minus A over 2, M equals T times Z. So you know how to do the one on the bottom. The one on the top is the pure axial from the column addition law that we did last lecture. And this point here is called the balance point, and that's when the concrete reaches 0, 0, 3, right when the steel on the other side it yields. So it's right at epsilon y, which is Fy over E. And this point over here is just when you make the neutral axis equal to H. So the far side is C. And so what I think we'll do in class is I'll pick these 3 points. We'll do these 3 in class tomorrow. We'll just pick those 3 um, and we'll go from there. Okay, and it'll be good practice. Or I think I'll pick one way out here as well. So maybe we'll do 4. Okay. But anyway, you vary the neutral axis, you do all this, you calculate it maybe 100 times, and you plot it. Well, doing something 100 times and plotting, that sounds like it's a job for Excel, which it is. And again, in a non-quarantine semester, that would be your homework, is to make this spreadsheet that does this, but we're going to skip that. I obviously have made these spreadsheets before. I'll just give you mine. Okay. But it is, if you like doing spreadsheets, it's kind of a fun thing. Next, the effective fee, the fee. If you remember way back when we talked about beams, phi was 0.9 if it was tension controlled. And for columns, phi changes to 0.65 if it's tied and 0.75 if it's spiral, if it's compression controlled. And we sort of glossed over it, but if you are in between tension and compression controlled, and it had to do with the strain in the steel, there was a linear slide from 0.9 to 0.65 or 0.9 to 0.75. This is where that finally comes in, and this is probably in the spreadsheet one of the more complicated things to do. But what it is, if the phi was constant, let's say it was 0.9, what that would do, it would be like you took your interaction diagram, put it in a photocopier, and said photocopy at 90%. But because the top half of it gets reduced by 90% and the bottom half gets reduced by, gets reduced by 10% to 0.9, and the bottom half gets reduced by 0.25 to 0.75, this happens. And remember, we said there's a minimum eccentricity, so you take, I can't remember the numbers, it was 0.8 off of the pure axial, or what was it, 0.75 off of, so 0.8 off of the pure axial for spiral, and I believe it was 0.75 off of the pure axial for tied. I can't quite remember. I'll have to go back and look at the slides. That's what this is. That reduction there. You take the percentage, and then you chop off the top. Okay. So anytime you see a moment diagram that has the top chopped off, and it does that, and what this reminds me of, I say it's like when a professor is wearing a belt too tight, it squeezes in his tummy. So if you see that where it's squeezing in over there, you can know that diagram already has phi applied to it, so you don't have to take your values and multiply it by phi. Okay, so if you see something like this, okay, the black one does not have the phi on it, the blue one has the phi on it. And so I have a spreadsheet that will make these for you. I have them with the phi and without the phi. You can use them, and but you can buy these things. Okay, and so if you have the textbook, in the back of the textbook, there's some that are there. This is one that I just found somewhere from an old textbook. Okay, you can buy these interaction diagrams, and see this one. It has that little pinch in by the belt. that little thing there, this already has the phi on it. Okay. And so this axis, the y-axis, that's phi pn divided by the gross area. And this one, okay, on the other side, okay, the x-axis is it's the y-axis times E over H, but you multiply that out, Pn times E, remember the definition of eccentricity was m over P, so P times E is the moment. So the x-axis is the moment capacity, but they've been sort of non-dimensionalized, divided by the area for the y-axis and divided by the area times h. Now the question is, which of the two dimensions is h? And it's always the dimension it's bending around, or you can look at the picture. Okay, and so that's H. And you need to look at the picture carefully. H is the dimension that's going from steel to steel in that picture. Okay, so the slope, okay, if you take y over x, can you see the slope is 1 over E times H? Does that make sense? Okay. The slope is phi pn over ag divided by phi pn over ag times E over H. So the slope is 1 over E over H. And so you can see that they've conveniently put in lines for you at constant slopes that represent the different E over H's. Okay, that is commercial interaction diagrams. But before you just start using these kind of crazy, I have some comments. First of all, match the shape. So when you look at these diagrams, they always in the corner will have the shape of the column. Some of them are round and some of them are rectangles. So that's pretty easy to tell that you're using the right one. But let me sketch the 3 kinds of interaction diagrams there are. So there'll be round ones. And this next 2 are the ones that you really need to be careful for. There are rectangular ones that have steel only on 2 faces, and then there are rectangular ones that have steel on all 4 faces. They are different, so you have to make sure that you're using the right one. If your columns have steel only on 2 faces, you have to match the picture correctly. Okay? Just make sure you're matching the picture. Okay? also match the direction. Okay. In these columns, the moment is going about the neutral axis in the direction shown right there. So the moment is going, let's see, this way on that picture. Let me get my hand right over it. Okay, right like that. It is not doing, let me move this over. So it's not doing this. It's not bending this way. It's bending this way. Okay? It's bending, I'm trying to, there we go. It's bending like this. Okay? It's not bending like this. Okay? They do have diagrams. Okay? That look like, the picture looks like this. And in this case, they are bending this way, which is a very ineffective use of your steel. So what you're going to have to understand is which way you've built the column in your building and which way the moments are bending that column in 3 dimensions. Okay, so this is not the easiest thing to do. So if you have your steel like this picture in the left, and the wind is blowing from left to right or west to east, then the moments would be acting this way. But if the wind is blowing north to south, then the moments are acting this way, like that picture. And so if you have moments in both directions, then you really ought to put steel in both directions, and that's why you would use these interaction diagrams. Okay? The ones square with steel all around. And this is the part of the project we didn't get into. It would have to do with how you design a lateral load resisting system. You would have gotten into this in your project in 4900, but we have to cancel that as well. But the main thing is match the picture and the direction. Okay. Be careful about the axes. Okay, it depends on what you buy. But look at that very carefully. I don't try to trick you. I just have only so many of these things that I can find in my books, and they're different. And some of them are like this, phi PN over AG. Others look like this. Okay, other ones, they throw a F prime C in the denominator to make it have no units. So be very careful when you use these diagrams to look at the axes to see what they actually are. And the last thing you need to be careful about is to check if the phi is already in there. And so it'll say in the axes, like this has the phi PN. Others will just be PN. But you can tell by the shape. If it has that little thing down there where it looks like the belt is too tight on somebody's stomach, then that has the phi in it. Oh, and there's one more thing you need to match. And this is why I have to keep looking for different versions of these. Let me erase all this. These graphs are for different gammas. Let me highlight that. Gamma is the ratio of the distance between the steel to the overall dimension. And that is not constant. It's because the bars are actually kind of big in columns. And so depending on the overall dimension of the column, if you have a very, very large column, gamma is high because the cover is insignificant relative to overall width of the column. But if the column is smaller, gamma can be lower. In this case, gamma is 0.6. It can go up to 0.9. Okay, and so that is how to use interaction diagrams. We're already at 30 minutes. I'll stop this video and I'll continue discussing these interaction diagrams in the next video.